All right, welcome to the Impulse and Change in Momentum help video. This is going to be an introduction to both impulse and momentum. We're going to learn the equations about them, and we're going to do a couple practice problems about impulse and the change in momentum. So, first things first, what is momentum? Momentum is represented by the letter P, and it's a little misleading because usually we think of momentum as M. We already have mass, and we're going to use this kind of cursive P here. So it's equal to an object's mass times an object's velocity. All right, so if we're going to calculate an object's momentum, it's the product of its mass, how large it is. That needs to be in kilograms. And its velocity, its speed, which needs to be in meters per second. So if we're talking about the momentum of an object, we do mass times velocity. What is impulse? Well, impulse, an object's impulse is basically what changes an object's momentum. All right, so if an object has a certain amount of momentum going in a certain direction and it encounters an impulse, the impulse is force times time. It's an amount of force applied to an object over a certain amount of time. Force needs to be in newtons, and time needs to be in seconds. Now, impulse and momentum are related to each other. How are impulse and momentum related? Well, again, if we're going to have a momentum that is being changed, it is changed by an impulse. An impulse causes a change in momentum. So when we start talking about a change in momentum, another equation that we use is m delta v. And delta v just means a change in velocity, because if you think about it, if the momentum is going to change, whether you're speeding something up or you're slowing something down or whatever, if you're changing the momentum, most often, in all the problems that we're talking about, most often the mass is not going to change. Okay, so if a ball is rolling down a hill and we want to change its momentum, we're probably not going to change the mass of the ball. Okay, what we're probably going to do is we're probably going to change the velocity of the ball. Okay, we would stop it or change its velocity from whatever it was when it was rolling down the hill to 0 when we put a force on it. So really this is one thing that we're going to be dealing with here, which is impulse equals a change in momentum. And so the change in momentum, P equals m delta v. That's what we're looking for. Now, again, impulse, we'll just use capital letter I, is force times time. And again, these are related to each other because, again, like I said, we need an impulse to change the momentum. All right, so a key equation here, something that we can do, is we can set impulse equal to the change in momentum. All right, and we'll put a little triangle here so we know we're talking about delta p change in momentum. So really what that equation ends up looking like is force times time is equal to the mass of the object. I'm sorry, I wrote that wrong. The mass of the object and the change in its velocity. So impulse equals momentum. Let's see how that plays out in a practice problem. It says a 4,500 kilogram automobile traveling at 40 meters per second stops in 2 seconds. How much force was applied to the car? Well, we have some information here. We have the mass is 4,500 kilograms. We have a velocity is 40 meters per second. And we have a stopping time of 2 seconds. And what are we looking for? We're looking for the force. Now, with that information, we can use what we just learned about impulse and momentum to kind of figure out what the force was. Now, one key thing we got to look at here is this velocity. Remember, we have a couple of different velocities that we can have. We can have an initial velocity, we can have a final velocity, we can have an average velocity. Well, what is it talking about? It says the automobile was traveling 40 meters per second. All right, so really that's going to be similar to what we've talked about before as an initial velocity of 40 meters per second. And then what's it going to do? It's going to stop. All right, so we really have a final velocity of 0 meters per second. Now, in our momentum equation, P equals m delta v. That delta v really talks about the change in velocity. Well, how much did the velocity change? Well, it was at 40, and now it's at 0. So really, this velocity can be considered our delta v, which is really our change in velocity, because 40 minus 0 would be 40. That's how much the velocity is actually being changed. So with that being said, we can get a little bit more specific here now as we link these two things together. So we have an m delta v, which is our change in momentum, and we learned just a second ago that m delta v is equal to the force times the time. So the change in momentum on this side is going to be equal to the impulse. Well, let's start filling them in. The m is 4,500 kilograms. The delta v is 40 meters per second. That's going to be equal to the impulse, which the force is what we're looking for. So we're going to leave it in as F. And the time was 2 seconds. Now this is simple. 4,500 times 40 divided by 2 seconds. You're going to get F by itself. And the answer that you're going to end up getting, if you go through this, we'll just do it quickly on our calculator. Reset. All right, so we had 4,500 times 40 on the left side. We hit enter. We're going to divide it by 2 seconds. All right, we're going to get 90,000 newtons. So we have 90,000 newtons would be our force. So we're going to go ahead and be able to realize that the applied force to the car was 90,000 newtons. That force was applied over 2 seconds, and that set our impulse equal to our change in momentum. All right, let's do another example. It says a person is hit in the head with a soccer ball that has a mass of 0.43 kilograms. The force of the ball on the person's head is 25 newtons as it was traveling 30 meters per second. What was the soccer ball's stopping time? So we are looking for stopping time. So let's start to break this down again. Same concept, looking for a different figure. You can see our soccer ball being stopped by a force right in our picture there. So let's start labeling some things here. We have a mass of 0.43 kilograms. That's that. We have a force of 25 newtons. We have a velocity of 30 meters per second. Now remember, we're going to call that delta V because it started at 30 meters per second. It's going all the way to 0, so the change in velocity is going to be 30 meters per second. Because it says the soccer ball's being stopped. It has a stopping time. And so what we're really looking for is we're looking for T, which is going to be the stopping time. All right, well, let's set this up again. Remember that m delta V, which is the change in momentum, is equal to the impulse, which is force times time. So we have 0.43. Let's label those correctly as kilograms times our velocity of 30 meters per second. We know that we have a force of 25 newtons being applied by the person's head, and we don't know our time. All right, so we won't take the time to show you on the calculator this time, but we end up knowing that our time, using some algebra here, multiply 0.43 times 30 first, then divide by 25, and you get 0.516 seconds would be your stopping time. And that's how impulse and momentum are related, along with